Great. As you can see, these are the topics that I plan to at least fly through, because there are too many to cover or do justice to, and involves several paradigm shifts one can refer to, beginning with Carl Pearson's descriptive statistics, Fisher's model-based statistical induction, graphical causal modeling, non-parametric statistics, and of course, data science, machine learning, and all that. And I begin with a quotation from Brayman, 2001, a very famous paper on the two cultures. And he basically says there are two cultures in the use of data in statistical modeling to reach conclusions from data. One assumes that the data are generated by a given stochastic data model. The other uses algorithmic models and treats the data mechanism as unknown. And he tries to provide a balance between the two approaches. Now, during the 20th century, statistical modeling and inference experienced all these shifts, and I am very selective. There were a few more, but these are the main ones. And what I'm going to try and show is that there is a link between these different shifts, with the exception of Fisher. So some of the key points that I'm going to be raising and arguing for is that the discussion on the replication crisis overlooks a major contributor to the untrustworthy evidence, which is basically statistical misspecification. When we do statistical inference, we do impose probabilistic assumptions on the data, whether we do it explicitly or implicitly, and if they are invalid, you get into trouble. So there is a direct connection between Carl Pearson's descriptive statistics, non-parametric statistics in the 1970s, and the more recent data science curve fitting. So prediction measures are really tricky when it comes to understanding what really is going on, because there are goodness of fit or prediction measures, and they are based on non-testable assumptions more often than not, and they're also invoking as n goes to infinity, and that creates problems of trustworthiness of evidence. Now, the major problem is what I call the curse. When empirical modeling relies on curve fitting of mathematical functions with a sufficiently large number of parameters to tweak, like neural networks and orthogonal polynomials, one will always find the best model on goodness of fit prediction grounds, even if that model is totally false. Worse, one will be oblivious to the fact that such a best model will commonly yield a trustworthy evidence. So best on goodness of fit prediction grounds means small residuals or prediction errors relative to a particular loss function. That is neither necessary nor sufficient for trustworthy evidence. What assures trustworthy evidence is statistical adequacy, the approximate validity of the probabilistic assumptions one invokes for the inferences. And that the totality of those probabilistic assumptions I call the underlying statistical model. Trustworthy evidence stems from procedures whose actual error probabilities approximate closely the nominal ones, the ones we derive presuming the validity of the model. That is, the trustworthiness of evidence originates in the relevant error probabilities as they relate to the severity principle. Now, all approaches to statistics share three basic elements: substantive questions of interest, however vague or precise, appropriate data to shed light on these questions, how we learn from data, and probabilistic assumptions imposed implicitly or explicitly on the observable process underlying the data. These are the assumptions that matter for statistical inference purposes, and not any assumptions one attaches to the error terms. How do these alternative approaches differ? In a number of different, let's say, components. The most important being inductive premises. How do we frame these inductive premises and how we interpret them? Model choice. How do we choose a model from that family of models that we always consider? Inductive inference, which is the underlying inductive reasoning and the nature, interpretation of their inferential claims. And lastly, and very important here, is how these approaches conciliate the substantive, the theory-based, and the statistical-based information. Now, here is a diagram that summarizes Carl Pearson's descriptive statistics. He begins with the data, he constructs the histogram, and then to find a nicer description of the data, he fits a curve on top of the histogram. He calls a frequency curve, and he proposed a family of such frequency curves or distribution functions, as we call them today, that this curve should belong to. And that's the Pearson family, we call it today, which is based on 4 unknown parameters. You estimate those using the first 4 raw moments from the data. And on the basis of those numbers, you choose a curve that belongs to this Pearson family. Of course, this includes a number of well-known distributions like the normal, students T, beta, gamma, and so on. So it's generally enough. But then you choose the particular frequency curve using a goodness of fit test, the famous Pearson goodness of fit. What Pearson and his contemporaries did not appreciate sufficiently is that irrespective of whether one is summarizing the data for descriptive or inferential purposes, one implicitly imposes probabilistic assumptions on the data. For instance, the move from the raw data to the histogram, which is the previous transparency from here to there, imposes independence and identically distributed. This is the most restrictive set of probabilistic assumptions. And of course, the same is true for the usual formulae that people use to summarize the data, the mean, the variance, the covariance, the correlation coefficient. And the first statistician who was puzzled and worked very hard to try to understand exactly what's going on was Ewell in 1926, a wonderful paper. I admire his tenacity to use reverse engineering, starting from this formulae to discover what are the underlying assumptions. And he did a very good job, but of course, he didn't really solve the problem completely for one reason only, that you need to understand what non-IID is, and that had to wait until the late 20s and early 30s for the theory of stochastic processes. And that, of course, were developed or initially with 2 Russian mathematicians, Kitchen and Kolmogorov. Now, can we charge Carl Pearson with ignorance? No, because it was too early to realize what random samples were and how to frame them in terms of probability theory. Now, what about the current discussions on the replication crisis? Yeah, I could charge these guys because they are now basically saying, well, if you interpret your statistics as descriptive, you don't have to worry about replication because you're not expecting replication. Having said that, the validity of the same probabilistic assumptions that underwrite the reliability of inference also ensures the pertinence of the corresponding descriptive statistics. Here I have an example. If your data look like that, and they are IID because I just simulated them, then if you use the sample mean and the sample variance, you will get numbers which are very close to the true values. But if you do the same thing with this data set, where the ID assumption is false, the data trending, then you're going to get stupid numbers. instead of 2 and a function of t, you're going to get 12. What about the variance? 34. The real one is 1. And of course, the same will happen if your independence is actually false. So one has to be extremely careful. Here I have dependent data. These irregular cycles indicate positive dependence. I go to the histogram and I do some, let's say, smoothing in non-parametric statistics later on, and you will see the true distribution is this one, and this is shifted to the right, and it looks bimodal. So the bottom line is when the IID assumptions are invalid for the particular data, not only the descriptive statistics, but also the estimated frequency curves that Pearson was fitting, as well as any inferences based on those statistics. So Fisher, well, 1922, a classic paper, he really turned Pearson's descriptive statistics on its head. Instead of beginning with a data set in search of a summary or a statistical model, he will interpret the data with respect to a pre-specified parametric statistical model. And this is really a generic form. Now, for those who are allergic to mathematical notation, I apologize, but after 40 years of teaching probability and statistics, I learned that if you water down all of this, you just create confusion. Everybody is familiar with the simple normal model where you assume normality and IID. And it turns out every statistical model in Pearson, in non-parametric statistics, in machine learning, always involves probabilistic assumptions from these 3 categories. This is extremely important because there's a lot of confusion out there. Sometimes the distribution assumption is indirect. Distance of moments, smoothness of the unknown density function, all of that. But it's there. And you have to look for them to understand what is it you're actually assuming. And of course, once you have these probabilistic assumptions, the joint distribution of the sample will be the foundation upon which you are going to derive the likelihood function and, of course, frequently statistical inference. So Fisher proposed a complete reformulation of statistical induction by modeling the mechanism, not the data, and framing that mechanism instead of a stochastic process underlying the data, not error terms or any of that. So in 1922, he says, how do we choose this statistical model? We ask a question of what population is this a random sample? That's the IID part. And adding that, and the adequacy of our choice may be tested afterwards. The adequacy here can be evaluated using misspecification testing. That is, we choose a statistical model to account for the chance regularities in the data, but its appropriateness is evaluated by comprehensive misspecification testing before we go on to do the inference. So, and the primary objective, this is also very important, of frequentist inference is really to learn about the true underlying stochastic mechanism, and I use theta star to indicate that true mechanism. So when theta star replaces the range of values, and you basically assume that that theta star, there is a theta star that could have generated the data. So learning from data takes the form of statistical approximations around theta star. Of course, it's unobservable, and we're not going to find exactly what it is, and framed in terms of the sampling distribution of any statistic, estimate or test statistic, and so on. And of course, this is the famous formula that made Fisher very, very influential, because he was the only one who can actually deal with these multiple integrals in the first, let's say, until the end of the 1920s and early 30s. Now, what is important here to note is that for frequentist inference, there are 2 kinds of underlying reasoning: factual, presuming that theta equals theta star, and hypothetical. That's usually for estimation and prediction, but for testing, we use hypothetical. Assuming that theta belongs to theta 0, that's the subset of the parameter space, or its complement. And this is really the underlying reasoning that drives frequency statistics. It's very, very important to know a few things. First, the statistical adequacy of that statistical model ensures that theta star lies within it, and thus learning from data is attainable. Neither form of frequencies reasoning, factual or hypothetical, involves conditioning on theta. And I'm flabbergasted when I read tons of papers. Theta is an unknown constant. You cannot condition on unknown constants. Has to be a random variable or an event. And of course, the third and most important, the decision theoretic for all values of theta in theta undermines learning from data, and in particular theta star, and gives rise to Stein-type paradoxes and admissibility fallacies. Misspecification. What happens when your statistical model has invalid assumptions? Well, your distribution of the sample is incorrect. So if you go there and substitute an incorrect distribution of the sample, and then you derive the sampling distributions of statistics, you are in trouble. You get into inconsistencies and sizable discrepancies between the actual and nominal error probabilities, and everything goes astray, including goodness of fit or prediction measures. How can I apply this particular approach to cases where one begins with a substantive model, a causal model or econometric model that I've been dealing with for the last 40 years? The answer is your first task is to bring out the statistical model implicit in this substantive model. There's always one, and you can dig it out very quickly. It is defined to be an unrestricted parameterization that follows from the probabilistic assumptions you impose again on the observable process underlying the data, and includes your substantive model as a special case. Here I have an example from economics. I'm going to show you examples from graphical causal modeling in a minute. So the substantive model is this one. You unscramble all the restrictions, unnecessary restrictions, and then you see that there are these obvious restrictions that take you from the statistical to the substantive. Now, of course, you can test a lot of these over-identified restrictions, as we call them, and that's part of the establishing the substantive adequacy of your model. Now, main features of the Fisher model-based approach. This is very quickly. The model is set, it comprises a complete, internally consistent and testable probabilistic assumptions relating to the observable process, and they come from three categories. And of course, it's a stochastic mechanism that is designed to account for the regularities of the data. How do we choose the model? Mean specification testing. That ensures that the actual error probabilities are very close to the nominal ones, and thus the trustworthiness of evidence. Inductive inference, this is the factual and the hypothetical, and this is what leads to learning from data about theta star. Its effectiveness, which is the optimality, and is calibrated in terms of error probabilities based on a statistically adequate model. Now, here I have a quotation of two famous, a mathematician and a philosopher, basically accusing frequencies from confusing probability of H given X0 with probability of X0 given H. The untutored think that they're getting the probability of effectiveness of a drug given the data, while they are being given conditional probabilities going the opposite direction. The untutored know from basic probability theory that conditioning on H naught, which is theta equals theta 0, is formally illicit, since theta is neither an event nor a random variable. So let's just bury that so we don't waste our time. Substantive versus statistical, well, they are related now. The substantive has been embedded into the statistical, and you can test these over-identified restrictions. And I'm going to go straight to examples. Here I have 3 examples, very simple, of course, just to be able to go through. The top part is the substantive model for a cofounder, collider, and so on. And what I do is transform these substantive models into statistical models. You have to establish the statistical adequacy of these before you play games with that. And of course, you can test the validity of your causal connections by testing these restrictions. So I'll run through that. Non-parametric statistics is interesting for my story here because it was the first attempt to replace the original direct distribution assumption with a non-directed distribution assumption. And of course, it gave us a broader family and a lot of, let's say, headaches. I'm going to skip that, only to read a quotation from Lecam about asymptotic inferences. Limit theorems, as n goes to infinity, are logically devoid of content about what happens at any particular n. All they can do is suggest certain approaches whose performance must be checked case by case. Unfortunately, the approximation bounds we could get are too often too crude and cumbersome to be of any particular use. Big data. So here is how Vapnik, a very famous contributor to data science in statistical learning theory, that's how he understands what he's doing. Between 1960 and 1980, a revolution in statistics occurred. Fisher's paradigm was replaced by a new one. This paradigm reflects a new answer to the fundamental question: what must one know a priori about an unknown functional dependency in order to estimate it on the basis of observations? In Fisher's paradigm, the answer was very restrictive. One must know almost everything. Namely, one must know the desired dependency up to the values of a finite number of parameters. In the new paradigm, it is sufficient to know some general properties of a set of functions in which the unknown dependency belongs. Now, this is a complete parody of what the Fisher model approach is, but that's really how they understand it. And of course, Fisher didn't say, this is the truth, let's go and do inference. He says, estimate the model, check its validity, and then you can talk about dependence and all of that. Actually, the dependence comes from the probabilistic assumptions. Here's a simple example. If I assume that YT, the stochastic process, is normal, Markov, and stationary, the dependence is an AR1 model. I actually get the parameters, the range of values, and everything from the assumptions. So we don't just write it down and run. We test the validity. So here is, let's say, the broader framework for machine learning. You start with the learner's input, which has, let's say, variables. Some of them are explanatory, some of them are, and so on. You have a training data, an unknown distribution, and this is always unknown. This is a black box, and learner's output. The learning algorithm here is all about choosing H to approximate closely the true relationship between the dependence according to Vapnik. By minimizing a distance. Now, where does that distance come from? Not from the likelihood function, not from the score. It comes from mathematical approximation theory, because all of this is embedded in, let's say, a mathematical framework from part of mathematics called functional analysis, which is the study of infinite dimensional vector or linear spaces endowed with a topology, metric, norm, inner product, and the probability measure. So you go into this high-level mathematics of norms and linear spaces, and this is how you define your distances that you're supposed to be minimizing. Here I have some well-known examples from that setup. Now, what's the advantage? Well,
You have 5 minutes.
You have a powerful setup with many interesting theorems, which can solve the approximation, let's say, problem that you set up for yourself. I'm going to skip the first part there and look at how supervised learning, which is what we call regression in statistics. Here you want to approximate a relationship between the x's, this is a vector, and the y, and of course you write it up with an error at the end. And the question is, how do you do it? Well, you have to choose a family G of smooth enough mathematical functions that will do the approximating. And of course, you're going to find out which one is the best by using a loss function. Here are two very popular loss functions. And of course, to get rid of x, for all values of x, you take expectations to define the risk function. And suddenly you have a mathematical problem in the context of a linear space, and you really need to solve it. Well, this is unobservable, so that's unobservable. So what do? Well, you use descriptive statistics. If I want the mean of something, I just take the sample mean, and that's what happens here. You approximate that with the sample mean of the loss functions, and then you minimize that to get the fitted curve, which is always inherently overparameterized. So what do? Well, you impose restrictions. And this is a typical example, easy to understand. This is linear regression, these squares, but then you just write to the right all kinds of restrictions to solve this overparameterization. And of course, this is all artificial. I'm going to skip that. Main features, I'll skip that. Weaknesses, curve-fitting curves, I've already mentioned it. I'm not going to mention it again. There are some really major confusions between data scientists and statisticians who work with patterns. The patterns a statistician will appreciate are these recurring chance regularity patterns, not fitting patterns that come from mathematical approximation. And here I have an example of what's going to happen if you want to do unsupervised learning, which is basically clustering, or fit a curve when your data are not IID. It's going to be a mess. So let me just
2 minutes.
Okay. Conclusions. Raymond's claim that in Fisher's paradigm, one assumes that the data are generated by a given stochastic data model refers to a common erroneous implementation of model-based statistics, where the statistical model is viewed as a priori postulated model presumed to be valid no matter what. That's not what happens. Here is Fisher, 1922, emphasizing how you should validate your model. The empirical is the specification of the hypothetical population, what I call a statistical model. Maybe this empiricism is cleared of its dangers if we can apply a rigorous and objective test of the adequacy with which the proposed population represents the whole of the available facts, the regularities. So our best bet for learning from data is Fisher's parametric model-based statistics with strong assumptions, but we test their validity before we do anything else. Frequency inference and this underlying reasoning will be the first to go from these statistics wars. Error probabilities and their key roles in securing the trustworthiness of evidence by controlling and evaluating how severely tested claims are, including statistical adequacy and substantive adequacy, will go as well. Misspecification testing and respecification, when you have a misspecified model, you need to respecify, that will go as well. And learning from data about phenomena of interest, minimizing a risk function to reduce the overall mean-square prediction error undermines learning from data about the true whatever generative mechanism.